And he has received the Mathematical Congress of America's Award in 2013. And he also received the Ramanujan Prize from ICTP in 2014. So his title of his talk is Characteristic Subsets and the Polynomial Method. Please.
Hey, hello. Thank you for the invitation. And the purpose of this talk is to talk about the polynomial method. This is a remarkably flexible approach that has been used to solve problems in a wide variety of fields. And what I want to do in this talk is to tell you about several examples of applications of this method, old and new, and what they have in common. So the method itself is hard to define. It essentially amounts to any proof that involves constructing an adequate polynomial. But what is interesting about the method is the similarities in the way that it is applied and the connection between the areas where it's used. In fact, one of the first goals of the talk is to emphasize how a lot of these applications can be phrased in such a way that they consist of two very precise steps. So let me begin by telling you a typical way in which the polynomial method is applied. So this is a typical form of the polynomial method. Two steps. Step one is given a set of elements S, which I will not tell you exactly what kind of elements I'm talking about. The whole point is that this is flexible and should apply in different contexts. Given a set of elements S, the first step many times is to find a small characteristic subset, A of S, such that if a small non-zero polynomial vanishes to sufficiently high order on A, then it must also vanish on S. So the step one is to find this thing that one can call characteristic subsets, a small subset of the bigger set that in a sense controls all the algebraic structure of this bigger set. So in order to find a polynomial that vanishes on the larger set S, it suffices to do so in the smaller set A that in this sense controls this algebraic structure of the set. This is the first step. And the second one is once we already located this small special subset A, is to use a dimension counting argument to actually find a polynomial vanishing on A. So use a dimension counting argument and the small size of A to show that there are small polynomials with nice properties that vanish on A and therefore on S. So step one, locate a characteristic subset that controls the whole set. Step two, use some sort of dimension counting argument to find a polynomial that vanishes in the smaller sets. Since the set A is a smaller subset, it should be easier to find properties, to find polynomials with nice properties that vanish on the small set and therefore on the bigger set. So I will tell you soon what I mean exactly by a dimension counting argument, but first, some simple notation that I will use throughout the talk. First of all, given a finite set A, I will write this for its cardinality. Second, I will use this asymptotic notation. Given two quantities x, y, we write this to mean that there exists an absolute constant c, such that x is less than that constant times y. And finally, given a polynomial p, which in this talk will always have real coefficients, I will write c of p for the zero set of the polynomial, the set of points x in R to the n, such that this polynomial vanishes. So this is all basic notation. And so as I said, the polynomial method has two steps in many of the applications. First, locate a characteristic subset. Second step, use a dimension counting argument. So the basic example of what I mean by a dimension counting argument is Siegel's lemma, probably the most basic tool in the polynomial method. It just tells you if you have any set of points, what is the degree that you can guarantee of a polynomial vanishing on this arbitrary set of points. So Siegel's classic lemma just says that given any set of points S in R to the n, we can always find a non-zero polynomial p of degree at most that, a constant times S to the 1 over n, that vanishes on S. So no matter what your points are, you can always find a non-zero polynomial of at most that degree vanishing on S. And the proof of this result follows what I call a dimension counting argument. It's just something extremely simple, it's just basic linear algebra. You just count how many polynomials there are of at most a degree. And there are so many polynomials of at most a degree that at least two different choices have to take the same values on S. Then you just consider the difference of those two polynomials, and you have the polynomial you want, a polynomial that vanishes on all each set of points. So it's just a dimension counting argument of how many polynomials there are. And in fact, in different applications of the polynomial method, there is a variation of this where you just find exactly what kind of argument you want to use for dimension counting arguments, and maybe you have some additional structure that you know about your set and you want to exploit this to find a polynomial with nice properties that vanish on your set. But it always boils down to a dimension counting argument of this form. So I will give you this as the first application of the method that I want to mention. is a very beautiful one because not only the result is interesting, but it happened to have a very simple proof that was unexpected. So the polynomial method was used by De Vere in 2008 to solve the Kakeya problem of finite fields with a strikingly simple proof. So before I tell you what's the result, just let me remind you quickly what the original Kakeya problem is. The original Kakeya problem is an unsolved problem that asks, if you're given a set K in R to the n that contains a unit line segment in every direction, then the assertion of the conjecture is that the dimension of this set has to be equal to n. The only way a set can contain a line, a unit line segment pointing in every direction, is for the set to have maximal dimension, for the dimension to be equal to n. Now, what dimension are we talking about? I'll leave it intentionally vague. It can be Minkowski dimension, it can be Hausdorff dimension. Either of those will be a fantastic result. The conjecture just asserts that whenever you have a set like this, it has to have maximal dimension. And the problem remained open for a long time, still open, and in order to approach it, Walsh suggested to study a finite field model of this problem, a toy model of this problem. And that is the question that was answered by De Vere. So De Vere's theorem says that if you ask the same question about a finite field, so let F be a finite field and K a set containing a line in every direction, then K has to have a maximal size. The size of K has to be at least a constant times F to the n. So it's clear that this is exactly the analogous question as the Kakeya problem over Euclidean space formulated over a finite field. The only way a set here can contain a line in every direction is for it to have essentially the maximal size possible. Now, what I want to emphasize is this was not a trivial problem. This was used as a model for the Kakeya problem, and there was a lot of interesting work done in this problem for around a decade. So the problem had remained open for a decade with important work on it carried out by Walsh, Bourgain, Katz, and Tao, among others. He developed, for example, to solve this problem, for example, the theory of sum product phenomena that is very useful in arithmetic combinatorics was developed to attack this problem. So it was not a trivial problem at all until De Vere found a solution that made it look trivial. It was an extremely simple solution, and the reason why he could find it is because he introduced the polynomial method. Now, De Vere himself, he came from theoretical computer science, where the polynomial method was a thing. It was not a thing here. And introducing that tool, he realized that tool goes exactly to the core of the problem. This is, in essence, an algebraic problem, and the polynomial method that's one of its main characteristics. It can be used in analytical problems to exploit underlying algebraic structure in those problems. So he used that two-step approach that I described before. So let me tell you how the proof goes. First step, locate the characteristic subset. What is the characteristic subset in this problem? His observation is that if a small polynomial vanishes on K, so in particular it vanishes on a line pointing in every direction of f to the n, that polynomial can be shown to vanish at all of f to the n. In other words, his observation is that a Kakeya set is always a characteristic subset of the whole space. So whenever you have a Kakeya set in f to the n, any polynomial that is small that vanishes on K has to vanish on the whole space. And let me just clarify that throughout the talk, a small polynomial can mean a lot of things. Usually it means that it has small degree, but it can also mean that it has small coefficients and things like that. The whole idea is that this should be a flexible concept. So his observation is that K is always a characteristic subset. And then just proceed by contradiction and use a dimension counting argument. So assume that the result phase-in, you can find a small Kakeya set. Then by a dimension counting argument, by Siegel's lemma, we can find a non-zero polynomial of small degree, in fact less than the size of f, that vanishes on K, and since it's a characteristic subset, it vanishes on the whole f to the n. So this allows you to find a small polynomial that vanishes in the whole space, which can easily be shown to be impossible. So this is all that it goes to the proof. It's extremely simple proof, even though the problem had been open for a while. And it uses this two-step approach that I told you. So what I want to do is to compare this proof with the most different result I can find that uses the polynomial method, which is also an old result, and it's Baker's theorem, at least one of its basic forms. So the polynomial method is old. It was already used by Baker to establish his famous results, the most basic of which is that if you have some set of non-zero algebraic numbers, and the logarithms are linearly independent over the rational numbers, then they are also linearly independent over the algebraic numbers. It's a very famous and important result of Baker. That again tells you that if you are given non-zero algebraic numbers, the logarithms are linearly independent over the rational numbers, and they have to be linearly independent over the algebraic numbers. So, well, of course, this result had a lot of applications. It was used to prove transcendence results, to study the class number problem, for effective bounds on definite time questions, and recently even to obtain effective bounds on Furstenberg's time 2 times 3 problem. in ergodic theory. The later is a paper by Bourgain, Linden, Strauss, Mitchell, and Venkatesh, which is, if you think about it, now it's a paper with 3 co-authors that are Fields medalists, which I will venture it's an odd thing. And these are a lot of different applications that this result has. Of course, a very fundamental result because it was given the Fields medal because of its work. But the proof, although it's in a very different context, it's worked in exactly the same 2-step approach that I mentioned before. So it will be good to compare with a much simpler proof in terms of how difficult it was to prove itself, which is the inverse theorem. The only observation here is that we have to understand exactly what is the context in which we are studying this problem. So here, the sets that we study, and this is a non-trivial observation, that this is the right set to study for this problem, but it's this sort of tuples. So the sets of the form gamma sub n, given by the elements of the form alpha 1 to the s, alpha 2 to the s, alpha r to the s, for s in the first and integers. So we study this particular set of points with the logarithms linearly independent over the rational numbers. That's the assumption of the result. So we proceed in the same way. First, we want to locate the characteristic subset, and for this we use the structure of the problem we are studying. In the case of the inverse theorem, we use that like a k set has a line in every direction to show that it's a characteristic subset. In this case, what is used is in some way the fact that this thing here are not arbitrary points, but that algebraic inters inside an analytic curve, so an extremely rigid set. So what can be shown is that in fact, even if you pick an n that is quite smaller than m, gamma sub n is a characteristic subset of gamma sub n. So Baker's first observation, although I mean this was a work by many people, Baker's find a way to do it in the final way to do this result, but it can be shown that gamma sub n is a characteristic subset of gamma sub n, even if n is quite smaller than m. And again, this is because of the structure of the problem. There are algebraic numbers inside an analytic curve. So there's a lot of rigidity, and vanishing on a small part of the curve implies vanishing on a larger piece like that. So first step accomplished, find a characteristic subset. Usually when you can find a characteristic subset, you're already in a good track to apply the polynomial method. And again, similarly how it was in the Beer's proof, you proceed by contradiction and use a dimension counting argument. So assume for contradiction that a linear dependence exists. A linear dependence exists over the algebraic numbers between the logarithms of these numbers, which is what we want to prove that doesn't happen. Assume for contradiction that a linear dependence exists. And this linear dependence can be used to boost the dimension counting argument. What this linear dependence actually accomplishes is that it reduces the dimension of the possible values the derivatives of the polynomial can take, and so makes the dimension counting argument more effective. So when you apply this Siegel's lemma boosted with this observation, this produces a very small polynomial that vanishes on the gamma sub n and therefore on the larger set gamma sum n. And once we have this, it's not only a small polynomial by the fact that it's a characteristic subset, but it's a very small polynomial because we also have this boosted version of Siegel's lemma. And so this produces a very small polynomial that vanishes on the larger set gamma sub n, and once you are in that situation, it's very easy to prove that that cannot happen. It just contradicts basic facts about van der Monde determinant. So you see these are two results in very different one and the other, but the method in which they proceed is very similar. So now my own personal experience with the polynomial method started with a question asked by Helfgott and Venkatesh. They asked to classify those sets that are very badly distributed in residual classes mod P for many primes P. So this is now, again, a question more like in analytic number theory. The distribution of sets in residual classes is a typical topic in analytic number theory. And they asked what seems like a very natural question, which is we are usually interested in showing that things are very well distributed in residual classes. They asked, well, what happens if something is quite the contrary? It's very badly distributed in residual classes. What can we say? And the conjecture is that they have some sort of algebraic structure, and some work was done on this problem using analytic approaches, like by Green and Harper or Hansen, which gives you some bounds on this problem. But it turns out that one crucial feature that sets that are very badly distributed in residual classes have is that they admit characteristic subsets. So again, it's the same theme as before. First step, locate a characteristic subset. I will not tell you exactly how this is done in this case, why is the reason, but to say that if a set is very badly distributed in residual classes, you can find a small subset that contains an unusual amount of representatives of the classes occupied by your set, and that can be shown to be a characteristic subset. Anyway, for the purpose of this talk, it just suffices to know that this is another context in which one can find this idea of characteristic subsets. And once one has this, one can just simply apply Siegel's lemma again to get a result of the following shape. So this is the simplest to state of the results that one can prove in this way. The main important thing is that such sets have characteristic subsets, and for example, that implies that if you have a set in n to the d, so in integers in d dimensions, that occupies p to the k residual classes mod p for every prime p, so there are p to the d possible classes, and your set occupies less than that, p to the k, then S lies in the set of some non-zero polynomial of degree at most a constant times this logarithm of n to the k over d minus k, which is essentially optimal. You can not get anything better than the power of log n. So this is another application of the polynomial method. You can always find a polynomial vanishing on any set that is very badly distributed, and the reason why it works, again, is because you can find a characteristic subset and then apply a dimension counting argument. So, as I said, this is how I got introduced to this problem, and this is where also I used the definition of what is a characteristic subset, which was inspired by characteristic factors in ergodic theory, which was a thing I was studying at the time, which has some similarities to this idea. And I thought that I didn't know it was a polynomial method, so later I thought, if they can put a name to what I'm doing, to call it the polynomial method, I can say that what they're doing is the characteristic subset. So I guess it's a fair thing. But one thing that this allows to show is that the polynomial method is robust. If you have a problem that can be attacked by the polynomial method, it's very likely that some problems that are similar to it can also be attacked. And in a sense, this is natural because what the polynomial method does is, in analytical context, it allows you to find the underlying algebraic structure. And there are not that many ways to do that. And the polynomial method shows you that the actual reason why the result is true is because there is some underlying algebraic structure in your problem. So if you have one problem that can be attacked in that way, and you have a similar problem, if the reason of the first problem to be true is that there is some underlying algebraic structure like that, that is not a surprise that a problem that is closely connected to it will also be subject to the same kind of approach, because the reason is probably similar in both cases. So a problem that is related to the distribution of sets in residual classes is, for example, the estimation of the number of points in curves and varieties. And this is another place where the polynomial method has been used, in fact, for quite a long time. The polynomial method has also been used to estimate the number of rational points in curves and varieties. In this context, it has been known as the determinant method. So that's another nice feature of the polynomial method that applies in so many places, and many of those different places has different names. In this place, it was called the determinant method, but it's essentially the same thing, with the difference that here, the emphasis is not so much in finding a characteristic subset, which is always implicitly done in an easy way. It's more about finding a good dimension counting argument. So here it was introduced by Bombieri and Pila to study integer points on curves, and subsequently extended by Heath Brown, Ellenberg, and Benkatich, Brown, and Salberg, and among others, to obtain estimates for rational points on curves and varieties. So the polynomial method in this form called the determinant method has been used in this area with quite an effect. And one particular yardstick of these results is to estimate the number of points of at most a certain height on curves. Particular result that one ends up with is the following. To give you an idea of what one can prove here using the polynomial method, there exists an absolute constant b, such that an irreducible algebraic curve of the rational numbers of degree d can have at most b times n to the 2 over the rational points of height less than n. So this is again a feature of the polynomial method. One, sometimes it can give you results that are quite easy to state. And two, there is this uniformity that comes with the fact that you're just using a dimension counting argument that is very beneficial in applications. So this particular result tells you that there exists an absolute constant b, such that an irreducible algebraic curve over the rational numbers of degree d can have at most b times n to the 2 over the rational points of height less than n. Doesn't matter what your curve is, the constant b is completely independent of the choice of curve. Any curve of degree d can have at most that number of points, and this can easily be seen to be sharp. And as I said here, the emphasis is on the dimension counting argument. For the proof, we combine an improvement of Siegel's lemma due to Bombieri and Baller with estimates of Salberger based on the Hasse-Weil inequality. So again, the emphasis is on the use of Siegel's lemma. There is a variation of Siegel's lemma that tells you can get a better dimension counting argument if you have a good bound for certain determinants of the system. Combining that result with good estimates on determinants obtained by Salberger, one can get to results of this form. Now, Salberger's result is based on the Hasse-Weil inequality, and again, I want to illustrate the point of how robust the method is. We started with the distribution of sets in residual classes. The polynomial method applies there. We move to the closely related field of estimating points on curves and varieties. The polynomial method applies there as well. We need to use the Hasse-Weil inequality. Hasse-Weil inequality is another example of something where the polynomial method works. So the Hasse-Weil inequality itself, the Riemann hypothesis for curves over finite fields, can be established by means of the polynomial method. Of course, it was not the original proof, but it was shown that this could be done in 1969 by Stepanov with an extension due to Bombieri to the full case. In this context, this technique has been known as Stepanov's method. So again, we start with distribution system residual classes. The method applies to estimating points on curves and varieties. And it also applies in something that we use there, and it's also quite related to these questions, which is the Hasse-Weil inequality itself. So just to mention quickly what goes into the proof here. Again, a characteristic subset is found implicitly by a very simple means. It's by an application of Bessoud's theorem that can be used to show that there is a characteristic subset. And finally, we want to fill an adequate polynomial during the proof. We want our polynomial to vanish to certain orders, and for that, we combine a dimension counting argument as in Siegel's lemma with the Riemann-Roch theorem. But again, it's always the same idea. You first locate that your problem has some structure that allows you to find a characteristic subset, and then you use some dimension counting argument that sometimes takes advantage of the particular problem you're studying to find an adequate polynomial vanishing on the characteristic subset and therefore on the whole set. So as you see, this is a method that applies again and again in different fields, and it's also a very robust method. Now, if the method is actually that robust, that brings us back to the first example I gave you, which is de Vere's theorem. If it applies to de Vere's theorem and the method is truly robust, it should apply to closely related problems. Could be the original Kakeya problem, could be the similar question of incidence geometry questions, which are of course very related to this kind of questions. And there is a way to, there is a common strategy of using exactly the steps I told you for the polynomial method, characteristic subset, and dimension counting argument. In that context, it's known as degree reduction. And what's nice is that does not apply to the points. It applies to, for example, if you're studying lines, you find a characteristic subset of the lines. And so if these lines are very connected, a polynomial vanishing on the set of lines, the fact that there are a lot of instances will give you vanishing on a larger set of lines, and the same phenomenon, but now applied to lines. But that is not enough to get the actual applications in this concept of incidence geometry. So in order to get the polynomial method to work, which it does in incidence geometry, Guth and Katz introduce an extension to study incidences between points and lines. So within a year, so of course, at the de Vere proof its result, there was a lot of interest in trying to find if that method applied to related problems. And Guth and Katz observed that a year after de Vere made his proof, that there is in fact a way to adapt the polynomial method to this context. And the difference here is that while originally, if you're given a set of points, one will try to find a polynomial that vanishes on all sets of points, their idea is instead of finding a polynomial that vanishes on the points, to find one that approximates the set of points. And approximate how? So I apologize beforehand of how simple this example is, but I think it illustrates the point. So what I do is I pick a line here, I pick another line here, and two more lines here. So that's the polynomial I want to construct. You see, it's not a polynomial that vanishes on the points I'm studying, but it's a polynomial that approximates the set of points in the following way. What it does is that it partitions the space into 9 cells, and each of the cells contains only 1 point. So I have 9 points, I can build a polynomial of degree 4 that partitions the space in 9 cells, and each of the cells contains only 1 point. And their observation is that this is a very general phenomenon. Again, by a dimension counting argument, one can show that there are so many polynomials of at most a certain degree that at least one of them will give you a very nice partition of space like this, where you start with some set of points and you can partition the whole space in such a way that each of the cells you create contain few points. This is a very robust phenomenon, very general phenomenon. You get a uniform bound for this kind of partitions. Why is this useful for incidence questions? Well, if you have a line, it may touch some of your points, but what you do know about the line is that if it's not contained inside the zero set, then it can only touch a polynomial of degree 4 in almost 4 points. So in particular, it can only touch 4 plus 1 of the components you have created. A line can only touch a polynomial of degree 4 in almost 4 points unless it's inside the zero set of the polynomial, and therefore it can only touch 4 plus 1, that is 5 of the components. And the same, of course, applies to any line. So if you're studying an incidence questions where you want to know how many times a set of points intersects a set of lines, they produce this very clever approach by which you partition the space in such a way that each part of space, each cell contains few points, and each line touches few of the cells. And then you can just use that and a trivial bound in each cell to get a good global bound. In a sense, this represents the intuition one has when one thinks that for the first time about incidence questions. Lines should just spread out across space and could not cluster somewhere. This is a formal way to see this. It is that you can actually partition the space in such a way that the points are distributed among space, and then the lines themselves can only touch a few parts of the space. So let me tell you again clearly what is the difference in this case, what is that they do in this case, given a set of points s in R to the n, and a positive integer m, another good feature, you choose the value of m. You can always find a polynomial p of degree at most m, such that each component of the complement of this polynomial contains at most a constant times the size of s divided by m to the n points of s. A polynomial of degree m can create at most m to the n components like this. And so this tells you that this is optimal even in that sense. You get an optimal partition of space such that the points are perfectly equidistributed among these components. This is a very general and useful result. Then you make the observation that the line can intersect at most Sn plus one of these components. And so you have reached the point where each component contains few points and each line touches few components. Summing a trivial bound among each component, we get a good global bound. So each cell contains few points, each line touches few cells. You can combine that with a trivial bound in each cell and you get a good global bound. The only problem here is that we have not ruled out the possibility that the points lie inside of the zero set of the polynomial. So I have told you that each component contains few points, but it may be the case that, well, that's true, but a lot of points actually lie inside the zero set of the polynomial. So the last step when you attack this sort of question, the last step is to deal with the points inside of the zero set of the polynomial. Which is not a bad thing because now you have an additional structure. You actually know that the points lie inside the zero set of a non-zero polynomial. So you have this additional structure to deal. In fact, for the people in dynamical systems, this is very similar to the structure randomness decompositions that are so useful there. You divide things into a structured set of points, those points that lie inside a zero set of a polynomial, and then a random part, which is those points that are just equidistributed along the partition that you have created, and you get the optimal bound in that case. But to deal with the points inside the variety, you need to exploit some other feature that the variety you're studying may have. This is a common feature of the polynomial method in some of its applications. You end up, because you have to create polynomial method, the whole point of the polynomial method, you end up studying what happens. Even if you're not interested in varieties, you end up studying what happens also inside varieties because of the very nature of the approach. So once they have that, they use it, among other things, to establish Erdos distance conjecture, this famous conjecture of Erdos. The theorem says that if you have n points in the plane, then there are at least n divided by log n distinct distances. So you have n points in the plane. They always create at least a constant times n over log n distinct distances. And the reason they could establish this is because by work of Felekas and Sharir, this can be reduced to an incident question between points and lines in R3. And the latter estimate was then established by Guth and Katz by means of their extension of the polynomial method that I just described. Back to the Kakeya problem. So we saw that I made the argument with the results in analytic number theory that the polynomial method is very robust. Different problems that are related with each other were admitted this same two-step approach to solve them. I said that maybe we should find something similar with diffuse problem over Kakeya fields, diffuse theorem over Kakeya over finite fields. We saw that there is a way to adjust the method to work for incidence geometry. What about the original Kakeya problem? So remember, the problem is if you have a set containing a unit line stemming in every direction, then the dimension of the set has to be maximal, has to be equal to n. And it turns out that the polynomial method can be extended to this setting. There is one important difference in this setting, which is that we are not dealing with a finite set of elements, which was the case in every other application I mentioned. Here, we have actually dealing with an infinite family of lines, and it turns out that in this kind of continuous setting, the polynomial method also works. It can be extended to continuous settings by considering the neighborhood of algebraic varieties, that is, for example, replacing lines by tubes. So the polynomial method can be extended to this continuous setting by considering the neighborhood of algebraic varieties. In fact, the Kakeya problem can be rephrased as a question about incidences between tubes. And using this, adapting the tools of the polynomial method to this continuous setting, Guth was able to obtain progress both on the Kakeya problem and the more general restriction conjecture of Stein in harmonic analysis. So there's a famous conjecture of Stein, the restriction conjecture, that among its consequences has the Kakeya problem. And these methods also extend to deal with that. So think about the fact that the polynomial method starts with a simple application to the Kakeya problem of finite fields. It reveals that there is some algebraic structure in the problem. And the method is robust indeed. You can go from there to incidence geometry, to the Kakeya problem, and even all the way to the restriction conjecture. And I guess one could argue that this is because the polynomial method is about emphasizing the fact that there is some underlying algebraic structure in the problem you're studying, and if that's the reason for a small part of the problem to be true, it may very well be the reason for some bigger part of the problem to be true. So once you see the polynomial method, and you have another problem that looks like what you just did, try to apply it again. So, okay. Now, as I mentioned, one problem that this has when we are applying the polynomial method is that even if we are not interested at all about algebraic varieties, we may end up actually having to study them because of the polynomial that we produce during the proof. So that's a common obstacle that I found in many applications and tried to do of the polynomial method, that if you end up having to have some sort of additional structure about varieties in general, and how to proceed in that case. So what one is interested in is obtaining versions of the polynomial method that work over general algebraic varieties. So let B in R to the n be an algebraic variety. It is possible to establish improved versions of the components of the polynomial method. So for example, the very first thing we saw is Siegel's lemma. To obtain a version of Siegel's lemma of a variety, that's easy. In applications, it turns out you don't only want that. You don't want to deal with just points, but general subvarieties. So the first result that one can establish is that we can find a polynomial of optimal degree vanishing on any set of algebraic subvarieties of B of given dimension and degree, and this bound improves with the degree of B. So Siegel's lemma, if you have a set of points, you can find a polynomial that vanishes there of optimal degree. What this result tells you is that if you have some general family of subvarieties of arbitrary degree and dimension, you can find a polynomial that vanishes on them. And of course, you can always do that because since you're there inside of a variety, you can just pick any polynomial in the idea of the variety, but we don't want something trivial. What we actually want is a polynomial that vanishes on a given set of algebraic subvarieties without vanishing on the whole of B. So one can establish an optimal bound in terms of the degree and dimensions of the subvarieties, and an important detail for the applications are that the bound improves with the degree of B. I'll tell you something about this in a second. Similarly, we want to do a polynomial partitioning, so what we do is we find a polynomial partitioning of optimal degree for any set of points inside the variety, where again the bound improves with the degree of B. Now, why isn't a very important fact that the bound improves with the degree of B? When you're attacking a problem like this, where you have to use the polynomial method in some of the ways I've described, you end up studying the question. Maybe you start in R to the n, and then you have to study some family of subvarieties. And it's usually the case that some of the tools you employ for your problem, while they may work well over R to the n, they may produce worse bounds as you deal with varieties of higher degree. So some tools that give you a certain bound over R to the n over varieties of high degree may give you worse bounds. So the whole point of having this sort of savings is that they allow you to cancel this out. So it's usually the case you start with R to the n, you cannot deal with the varieties because things get worse, but there is this underlying phenomenon on the other side that tells you that while it does get worse on one side, it gets better on another one, and this is what allows you to glue the whole thing together and get results. So these are some sort of applications. The third one, some sort of result, the third one is of a more real algebraic geometry nature. So for example, we saw in the description I gave you of the Kuth-Katz method that we wanted to know, it was important to know that lines can only touch a few components. Of course, if you're asking more general questions, you may wonder, you may have to know how many components can a variety of general degree and dimension can touch. Not just the line, which is easy, but how many components, like I described before, can be touched by an algebraic variety of certain degree and dimension. And it turns out this question is actually equivalent to estimating the number of connected components of real algebraic varieties, which is a classical topic going back to the work of Milnor and Thom, and more recently with a very strong result due to Barone and Basu. But the point of this, the one aspect in which these results do not end up being entirely useful for the problems at hand is because the bounds for the number of connected components in the literature depend on the maximal degree of the polynomials you're studying, while the saving that I mentioned before that we have in this sort of problems depends on the algebraic degree of the variety, which can be much smaller than what you get using just the maximal degree of the polynomials. So the point of the third result is to actually get an estimate that is sharp over a cover. I will not tell you exactly what I mean by a cover, but the point is that you get a bounds for a number of connected components of real algebraic varieties that are sharp, and they depend not on the degree of the polynomials, but the actual degree of the algebraic variety. And that way, in the applications of the polynomial method, what you lose, since it's sharp and depends only on the algebraic degree, can be cancelled out by the savings I mentioned before. So that's, and well, I won't tell you what the cover is, but it turns out to be something that it's just what we need for the applications. And so these different things allow you to improve a little bit on the polynomial method and allow you to get some new results. One result that combines all three things is an extension of what I mentioned before. So using this allows you to not have to rely on some special properties of the varieties you create, but it's just some soft approach that applies in a unified way in all of this. So for example, as an application, we can establish a general incidence estimate over any variety for any set of subvarieties of arbitrary degree and dimension. So as you have the result for points on line, you can extend this to deal with not just lines, but any family of subvarieties. Of course, there are many results in the literature in incidence geometry with different bounds of this form. This is an example of a general result that gives you exponents that depends on the dimension and with an explicit dependence on the degree of the varieties, and it's a general result that is sharp in every case. So this is one way in which these refinements can be applied, and there are others. But what I want to finish the talk with is just a small remark. I have mentioned how the polynomial method is very robust and how it applies to a lot of different fields. On the one hand, you have these results in analytic number theory that are connected with each other, and you have this other line of research having to do with Kakeya sets and incidence geometry. Now, I guess that for the purpose of this talk and the examples I've chosen, it's important to just make a small remark and then with that, which is that in analytic number theory, the topics that I mentioned are related to other parts of it, like the study of exponential sums, the exponent pair conjecture, and things like that. In particular, the Montgomery conjecture is the one I want to mention, because I want to argue exactly the contrary of what I've been telling you. I told you the polynomial method is something that is very versatile and applies in a lot of different fields. I want to now make the opposite argument. So in analytic number theory, one of the lines I haven't mentioned, you have this famous and very powerful conjecture of Montgomery. Let me just tell you what it is. For any real number R and any sequence of complex numbers that are uniformly bounded, we have a conjecture that we have an estimate of this form. So on average, exponential sums cancel out. Of course, this is clearly inspired by attempts to try to make progress in the Riemann hypothesis that this kind of exponential sums cancel on average. This is Montgomery's conjecture, at least in certain ranges of the parameters. And so, of course, this is a central conjecture in analytic number theory and has to do with one of the line of research I have been discussing today. On the other hand, I mentioned the problems of Kakeya finite fields in geometry and so on, and it's a well-known fact that, in fact, Montgomery's conjecture also implies the Kakeya problem. So you see that this is where both lines of research meet. These different places where the polynomial method applied are in fact different problems, but they end up being somehow connected in this way. And in fact, the connection works both ways. The connection also works the other way, with a decoupling theory developed by Bourgain and Demeter to study restriction problems leading to applications in analytic number theory. Include a proof of the Vinogradov's main conjecture and the best known exponents on the Lindelof hypothesis for the elements of the function. And so you see that you can make both cases. So in conclusion, one can see the polynomial method as an extremely versatile tool that applies in a lot of different fields. But one can also see it as a way to exploit the common underlying algebraic structure in a lot of very interesting interconnected problems. So I hope that in this way I have given you some feeling of why the method is interesting, how robust it is, and why the areas where it applies are also quite interesting. Well, thank you for your attention.
Thank you very much. Are there any questions, comments?
So when you say something like characteristic set, it sounds familiar to the characteristic factors from ergodic averages. And you mentioned something about dynamical systems applications, talk about the structured part and random part. But I was wondering if some of the machineries you discussed here have some applications in ergodic averages per se, if it touches something.
What's the last part? I'm sorry.
I was wondering if there's some of the things you discussed here have connections with ergodic theory, particularly in ergodic averages, or.
Well, no, I mean, there are two things to be said that which is more, I won't say anything new I haven't essentially said in the talk. The first one is that there is this, for example, application of this polynomial method applies to Baker's theorem, and then this applies to obtain effective bounds and things like that. That will be one way of application. On the other hand, many of these things that I discussed are quite similar. Like, for example, the partitioning theorem itself that I mentioned is a form of the regularity lemma, which, while it's not directly something that you use in ergodic theory, it is very, very close connected. But it will be very interesting to find some application. It seems to be very close, and maybe there is something that can be applied that is new, that happens first inside ergodic theory, not some secondary indirect application.
Other questions? Comments? Okay, if not, thank the speaker again.
Thank you.